Okay, so just as a reminder from last week, we talked about cognitive load. We talked about that cognitive load is a result of the limited capacity of the short-term or working memory. You have to really lean in there, Jonathan. You okay? Can't hear me?
I'm competing against a Hoover vacuum. The vacuum will be finished in about 4 or 5 minutes, but for now I can hear as long as my ear's next to the speaker. Sorry.
No, that's fine. I wanted to make sure you didn't pass out, like fall asleep or something. So we talked about how cognitive load is sort of what's in our conscious thinking, and it's limited. That's the model, and it's made up. One of the models is the theories is, and again, these are all theories. In reality, scientists haven't actually found a place in the brain that's called your cognitive load or your working memory. Like these are all theories that are helping us make sense of some of the results that we're seeing from data. But in the world of cognitive load, we often hear about sort of intrinsic load, which is load that comes from the content itself. Things that if things are overly new to us, or we're not fluent with them, then that increases our intrinsic load. If things are too new, too unknown, extraneous load comes from sort of the what's happening around the learning, how the learning is presented, the classroom environment, yeah, things like that. Okay, and whatever's left, we try to minimize extraneous, but we try to optimize intrinsic. I didn't say this last time, but too much intrinsic and we get overwhelmed. Too little intrinsic, students get bored. So it's the challenge within the intrinsic load. And here's a problem for you to try to solve. Okay, here's a problem. 4 cards. Each card has a letter on one side and a digit on the other. There is a rule. If there is a vowel on one side, there must be an even number on the other side. Your job is to verify whether this rule is met for this set of 4 cards and to turn over the minimum number of cards necessary to do so. Which cards do you turn over? Anybody want to try to answer?
I would turn over A and 2. So I'd turn 2 cards.
Would you not have to turn all 4 because you need to check that there's, oh no, bear with me. Yeah, do we not need to check that there's an odd number behind A and B? No, behind B, an even number behind A vowel behind 2, and a consonant behind 3. If we wanted to see all 4.
Okay, let's try. Let me give you a second problem. Imagine you are a server at a bar. Each card represents a patron who comes in with an age on one side of the card and their drink on the other. You are to enforce this rule. If you're drinking beer, you have to be 19 or older. Your job is to verify whether this rule is met for this set of patrons. You should turn over the minimum number of cards necessary to do so. Which cards do you turn over?
For that one, you'd only need to do beer and 31 because it doesn't matter who's having Coke. Or, oh no, you'd have to do 17 in case it's got beer on the other side.
Do you have to do 31?
No, because they can drink what they like. Oh, okay, beer and 17.
Okay. Easier to answer?
Yes.
Okay. What makes it's the exact same question. Literally the exact same question. What makes problem 2 so much easier to solve than problem 1?
Can you bring us back to problem 1? Oh, yeah. The second card has a 2 already, so the rule's not broken if there's a consonant on the other side. And for
So yeah, so it's the
and
exact
for
same.
B, the rule's not broken because there's it's not a vowel, so it doesn't have to
Don't
have an
care
even
about
on the other
vowels.
side. So just A and 3.
Yeah.
Yeah, I've
Just
seen this
helpful
before. It's
for-
still hard.
And yet this one, pretty simple. Okay. So why are we able to do number 2 so easily, or more easily?
Because we can contextualize it and visualize people in a bar drinking beer.
Yeah, yeah, exactly. So thinking about problem solving, Daniel Willingham is one of my favorite cognitive scientists, writes that people actually draw on memory to solve problems. We draw on memory much more to solve problems than we actually think. We often hear about problem solving being a skill, being something that we get better at generally. We're going to kind of get into that today. For example, among the world's best chess players, it is not their ability to reason about the game or to plan the best moves. Rather, it's their memory for game position. So there's lots and lots that comes out of expertise research. Chess is a big one. But what's interesting is chess masters, if you show them a board, they can memorize, and you give them 5 seconds to look at the board. They can recreate the board very quickly, much more than a novice can. What's interesting is they can only do it if the game pieces are following the rules of the game. If you randomly put game pieces on the board, chess masters can't create that mental representation of it. And the reason is, it's not that they're better at visual learning or memorizing visual things. It's the fact that they look at the board and they see the millions of moves that they've done in the past represented. And so they're able to see patterns and schema on the board. It's not their ability to sort of memorize the board. So what we're talking about here is a little bit around problem solving. And there's sort of debates and discussions back and forth, and we even see it played out kind of at the core of our curriculum around our core competencies. Is problem solving, is it a general skill? Is it something that exists between what we know and the different subjects that we learn, or is it kind of deeply connected to domain specific knowledge? Even think about your own experience for a second. Do you have experiences where you get better at one thing? So maybe, you start to, lately I've been trying to play piano the last couple of years and get better at playing piano. Does that mean that that automatically transfers to me to be able to do fix cars better? Not necessarily. And so there's different sort of what they call near and far transfer of knowledge and expertise that we gain in an area. So here's a couple of, I really like a couple of books from the National Research Council that kind of summarize a lot of the cognitive science research of the last decade. This is a pretty tough quote. It says, over a century of research on transfer, so transfer being the ability to apply learning in new situations. So Anthea, we were talking about spelling, right? Being able to take a spelling list and then apply that to a story writing is what we would call transfer. It's called near transfer because the context is similar. So over a century of research on transfer has yielded little evidence that teaching can develop general cognitive competencies that are transferable to any new discipline, problem, context, in or out of school. So that's difficult to hear. Nevertheless, research has identified features of instruction that are likely to substantially support deeper learning and development of 21st century competencies within a topic area or discipline. For example, we know that transfer is supported when learners understand general principles underlying the original learning and the transfer situation. or problem involves the same general principle. So the idea is, one of the themes that seems to come out of research is we're best talking about problem solving, critical thinking, deeper thinking, all within the context of disciplines. And I think from a common sense perspective, that makes sense. I mean, somebody who spends their lives becoming an expert in Canadian history and developing incredible depth of critical thinking with historical research, it doesn't mean that they can now become critical thinkers in molecular biology or, or cooking or any of these things. There are some general dispositions that help habits of mind and such, but even the ability to apply those are really, as we're going to see, really based on the knowledge that we have. Anders Ericsson is kind of one of the world leaders in researching expertise. He coined the 10,000 hours rule, if you've ever heard of that. Malcolm Gladwell wrote a book of kind of on his work. And basically from his work, what we learned is that novices and experts solve problems differently based on their ability to mentally represent the problems. Novices look at the surface qualities. Experts identify the underlying laws or concepts. So again, if you think of the chess example, a chess master can look at a board and see patterns of game movements. They don't see pieces. They see sort of collections of past situations and how those represent the best moves. They call it situation and action. They can they can see a situation and know what the right action is. So for experts, pre-established schema allows them to more quickly categorize a new problem and link to correct strategies or solutions. They're able to see how a new problem is a novel case of a previous problem. So it's not as though any expert is a better problem solver. We go back to our Canadian history example. It's not as though they have developed some general thinking skills that others don't have. It's that they have drawn on and built the ability to see underlying concepts when they approach a historical document or text. And that all kind of shapes how they approach this new situation. If you think of a car mechanic, same thing. They're drawing on all their past experiences and knowledge. I saw an interesting little summary of it in a book I was reading yesterday that I thought captured it well. Novices use problem-solving strategies. Experts use knowledge. So if we don't know something, we have to go through trial and error or guess or, ways that are inefficient. But experts are able to actually draw on their past knowledge in order to solve problems. Here's an example that comes out of the research. This is kind of a classic one. By Sweller, the guy who started a lot of the cognitive load research. And this has been replicated. This was from 1985. It's been replicated dozens, many times over the last few decades. But basically, you give experts and novice physicists some problems, and you ask them to categorize the problem. And novices will categorize them based on the surface features. So whether the problems are using inclined planes or whether they're bridges or springs but experts categorize problems based on the underlying principles, whether the problem requires conservation of energy or Newton's first law. And so basically what happens is our expertise, as we get better in an area, it actually changes what we notice when we see a problem. We don't see it as this engineering problem as a bridge problem. We see it as a conservation of energy problem and then so we can draw on our understanding of that. So experts see past the surface details and they apply pre-existing schema. Okay. So then how do we get better at problem solving? One of the key, and again, kind of challenging ideas that I find challenging, it's come out of cognitive science, is that we actually, it seems to suggest we actually don't get better at learning to solve problems by practicing solving problems. So how we, in the first line there, how we solve a problem is different than how we develop a schema. So let's talk, a simple math question. If learning how to add 2-digit numbers, how we build the understanding of what's happening in that skill or bundle of skills is how we develop that is different than how we apply it to a problem. And we can't, the research is saying we can't build it through just practicing problem solving. We have to have some of that understanding before we can do the problem solving. The problem and being engaged in problem solving and applying knowledge helps us kind of strengthen it, retrieve it, connect it, all of those things. But it doesn't necessarily, it's not how we build it. And part of the cognitive load research is that, as I said earlier, general problem solving approaches like trial and error, things that novices do, are often slow and inefficient, and often they don't even lead to new learning, even if successful. So if I'm not an expert in something, like let's say my dishwasher breaks, and I'm horrible with anything mechanical, I might just try a whole bunch of things. And I may solve the problem, but at the end of the day, I probably haven't come away with a better understanding of how dishwashers work. Chances are I've just kind of hacked my way through the problem. Right? So how do we get better at it? Dylan William, who I quite like, he talks about that the reason that people are good at what they do is because they have lots of knowledge that is well organized, able to bring it up at a moment's notice in response to a particular issue. Skills are important but not transferable, and this is kind of another kind of, I find very provocative. The mistake that we've made is believing that people need to improve their thinking skills. Rather, what we need to give them is more stuff to think with, more cognitive material, better schemas, better understanding, better conceptual understanding. So if we want kids to get better at problem solving, and what this theme of cognitive science is saying is we actually have to have them build up more rich bases of background knowledge that are kind of well organized around conceptual understanding, not more opportunities to just practice problem solving in a general sense. One last slide here, and then we'll give you a little bit of time to think. So if knowledge matters, what kind of knowledge transfers? I found this kind of a helpful table that if we want factual knowledge to transfer, it has to be integrated. So it has to be connected to big ideas. It has to be built around a concept. And so, which is good reason to be sort of teaching units around big ideas. And I think our BC curriculum's made an attempt at that, is sort of to have these big ideas. I know we've kind of lost talking about them quite a bit, but those big ideas in theory are there to help structure kind of the knowledge and skills around a discipline. And so we want to integrate knowledge around big ideas and big questions. Conceptual knowledge, for it to be transferable, needs to be sort of schema. It has to be models. It has to be around principles. And abstraction. So being able to sort of learn things and then build abstracted ideas that can be applied elsewhere. Procedures for them to transfer need to be automated, fluent. So we think of, in the world of math, the more fluent some of the foundational procedures are, the more easily transferable they are. So students aren't like thinking about them every time they're solving problems. Strategies, this is a really interesting one too. There's lots of work around metacognitive strategies and self-regulation strategies that are the research. There's quite a bit of research that says they are far more useful when they are domain specific. So in teaching students to self-reflect within the world of history or math or science is more impactful, and asking students to be metacognitive within, what good writing is, and giving them the tools to know what good writing is more impactful than talking about metacognition in a more general sense. And then lastly, beliefs are transferable beliefs are sort of productive beliefs about learning. So having a growth mindset, having a belief that you can get better. So that's a whole bunch of information. Take a few minutes there and just kind of soak all that in. How does that align with your current thinking or beliefs on problem solving? What's confirmed in that? What is challenged or provoked? And then what are some of the implications for your teaching? I'll stop there and just give you a couple minutes to think through that. And if you have any thoughts or questions, you can definitely drop them in the chat.